we're going to deal with the molecular shape. The important thing is that we have 1, 2, 3, 4, our central atom, bonds, no extra pairs of electrons, so we're just going to leave it at that and go right away to our molecular shape table, where again we're dealing with a SN, steric number of 4 pairs of electrons, and here it is, tetrahedral, and it's an sp3 hybrid, and we've got roughly 109 degrees, the best way to separate electrons or anything from one another in 3 dimensions. It's that tetrahedral shape. So that's going to be pretty easy. That's what we expect. And let's take a look at that shape. Again, the flat diagram indicates 90 degrees, which makes these fluorines too close together. If you give them a chance to separate in 3D, this is sort of more of a 3-dimensional drawing that you get. Now, this is the one that the flat one is what they'll show you on the AP exam. We've got 109 degrees for all of these, and here we are. This would be its shape, and let me quickly go to a device here. Let me see, where is it? Our 3D generator, so you can see this a little bit better. This is a commonly used generator that shows you what a tetrahedral structure, in this case silicon tetrafluoride, looks like. You can see the electron clouds are all opposing one another. You can look at this in terms of tubes also in 3 dimensions, and even wires, and the view of what the electrons would be like as clouds on this. We'll show and use this a little more when we deal with organic chemistry, but there you get sort of an idea of what the tetrahedral shape sort of looks like. So let's go back to here and try and figure out the polarity that's involved with this. I'm going to get my arrows here, and we've got a tug of fluorine. Remember, our very, very highly electronegative element, 4, compared to silicon, which is way down here, is 1.8. So silicon doesn't stand a chance. This pair of electrons in this bond would be really favored and very, very close to the fluorine. And if we had just one bond, the fluorine would be very negative, almost ionic, and the silicon would end up being positive. But we've got a fluorine tugging on this side, we've got a fluorine tugging on this side, and up here too. And all 3 of these together would cancel one another out. Even though we've got this tremendous difference in bonds, they tug in such a way that you're not going to end up having any polarity. The dipole moment of silicon tetrafluoride is 0. So remember, we've got polar bonds, but no dipole moment. Now I'm going to bring up one other little thing that's sort of a sneak preview of what's going to be happening. Let me pull up silicon tetrafluoride in terms of the Wikipedia, and here are 4 tetrahedral compounds of silicon trihydride silane, the tetrafluoride, the tetrachloride, the tetrabromide, the tetraiodide, the halogens. And notice their boiling points, 100 degrees below 0. And that boils at a really low temperature. You're going to have this at a gas at room temperature. 90 degrees, a little bit warmer. But now all of a sudden, with 4 chlorines, still a dipole moment of 0, we've got a boiling point of higher than room temperature. This is degrees Celsius, not Kelvins, naturally, because we have a negative. 60 degrees, and then 150 higher than the boiling point of water, and 290 Celsius. That's like 400 Fahrenheit. The boiling temperatures go up significantly as we have larger molecules involved in this, and we'll see, like I say here, a lot more about this later, and use an explanation that involves London dispersion forces in the future. So sneak peek as to why shapes of molecules are important, and silicon tetrafluoride.